Hello, next we are going to discuss about fast Fourier transform or FFT. It is an efficient method to find the discrete Fourier transform with the minimum number of calculations. That means, suppose we have to find a 4-point DFT. 4-point DFT, then that will be very much easily to find the 4-point DFT by using corresponding equation for DFT method. Okay, but as the number of point increases, say if suppose we are going to find 8-point DFT, then the number of calculation steps that will be increased. Okay, again, if we have to find the 16-point DFT, the number of calculations will go on, keep on increasing. So that will be more difficult for us to solve the questions by using ordinary DFT method. For that purpose, we are using fast Fourier transform. Fast Fourier transform is an efficient method for computing DFT itself. But here we are using some algorithms or steps. Okay, right. The computational efficiency is achieved by using divide and conquer approach. Okay. The meaning of divide and conquer is, suppose we have to find an 8-point DFT. Just take a look at this block diagram. Here we are going to find out the 8-point DFT. Then we will get 8 answers: x0, x1, x2, x3, x4 up to x7. That is 8-point DFT. In divide and conquer approach, we are dividing this 8-point DFT into two 4-point DFTs first. Here we have to find 4-point DFTs. Two 4-point DFTs together combining, we are getting a single 8-point DFT. Then further we divide these 4-point DFT into two 2-point DFTs. Okay, then we are getting two 2-point DFTs. For a single 4-point DFT, we have 2-point DFTs, and again the bottom 4-point DFT is again subdivided into two 2-point sources. Sorry, 2-point DFTs. Here we have 4 2-point DFTs total. Okay, first one, second, third, 3 and 4. Can find the 2-point DFT very much easily. Okay, by combining the outputs of these four 2-point DFTs, we are getting two 4-point DFTs. 1, 2. Okay, again by combining these two 4-point sources, we are getting a single 8-point DFT. Okay, this is the meaning of divide and conquer approach. അപ്പോൾ 2-point DFTകൾ കമ്പൈൻ ചെയ്ത് 4-point DFTകളാവും, 4-point DFTകൾ കമ്പൈൻ ചെയ്ത് 8-point DFT കിട്ടും. അതാണ് ഡിവൈഡ് ആൻഡ് കോൺകർ അപ്രോച്ച്. ഓക്കെ, ക്ലിയർ ആയില്ലേ? Okay, that is the meaning of divide and conquer approach. In order to perform a radix 2 FFT algorithm, n should satisfy this condition. N is equal to 2 raised to m. This 8-point DFT can be found by using radix 2 algorithm because this 8 can be expressed in terms of 2. That is n is equal to 2. If we substitute, we will get 2 raised to m. Okay, 8 is equal to 2 raised to 3. All of you know that 2 raised to 3 is equal to 8, right? Okay, means we can express n in terms of this equation. Okay, right? Then where m is the number of stages. Okay, number of stages required for computation, or otherwise number of computational stages, that is denoted by using m. That means in order to perform an 8-point DFT, number of stages required is equal to, here we are getting m is equal to 3. So there are 3 computational stages required. Okay, 3. To find out an 8-point DFT using radix radix to FFT algorithm, we need 3 computational stages. In order to find an 8-point DFT, we found that the number of stages required is 3. Okay, this is the first stage of computation in which we are finding 2-point DFTs. Okay, this is our second computational stages in which we are finding 4-point DFTs, and finally in the third stage we are combining these 4-point DFTs to obtain this 8-point DFT. Okay, right. This one is first stage, second stage, and final stage, third stage. Total of 3 stages are required for computation of 8-point DFT. Next, we are going to compare the computational complexity in both methods. If we find, if we calculate DFT using ordinary method, means by using corresponding equations, then the total number of additions to be performed is n into n minus 1. For multiplications to be performed is n square. And if we use the radix 2 FFT algorithm, then the computation complexity can be very much reduced by this factor n into log to the base 2n, and number of multiplications included is equal to n by 2 log to the base 2n. And now let us demonstrate this concept. Okay, suppose n is equal to 2. That means now we are going to find the 8-point DFT. For 8-point DFT, n is equal to 8. If we find 8-point DFT by using ordinary method, the number of additions included is equal to n into. So if we substitute 8 in this equation, we will getting 8 into 8 minus 1. That is equal to 56, and that of multiplications included, number of multiplications is equal to n square, means 8 square 64. If we continue this process using ordinary FFT method, this is ordinary DFT method. Okay, ordinary DFT. Now if we perform the same operation using radix 2 method, number of additions is equal to n log 2, 8 log 2 8, that is equal to 8 log to the base 10, 8 divided by log 2. This because log to the base 2 is not available in our calculator, then 8 log 8 to the base 10 divided by log 2, okay, to the base 10. Okay, right. Then we are getting the result as 24. Okay, then the number of multiplications that is equal to n by 2, then 8 by 2 log to the base 2, okay, log 8 to the base 2, okay, right, that is equal to n by 2, 8 by 2 is equal to 4 log 8 to the base 10 divided by log 2 to the base 10. Okay, the result we are getting is 12. Just take these comparisons. Okay, if we are using ordinary method, the number of additions is equal to 56, and if we compute using radix 2 algorithm, that is only 24 additions. Okay, and again, if we compute using ordinary method, the number of multiplications to be performed is 64. At the same time, if we are using this radix 2 algorithm method, number of multiplication to be performed is only 12. Okay, that is the meaning of the reduced number of calculations. Okay, right?